Hello, today I'm speaking with Augustine Mavor Parker, who graduated from the foundational AI CDT this year as part of its first cohort. Welcome, Augustine.
Thanks for having me.
So, at a high level, can you tell us what your research was about at UCL and what was the title of your thesis?
Yeah, title of my thesis was investigating sample efficient reinforcement learning. Um, I'd say I started my PhD in 2019, so this was before the sort of hype of LLMs in RL. So back then we were just doing RL basically to train agents to play mostly Atari games. Um, and kind of by necessity, the thing I had to work on was trying to make them learn to play Atari games more quickly because I didn't have, masses of compute resources. So um, kind of had to figure out, ways to get them to train more quickly with the sort of resources that I had. And um, essentially what that sort of, the main thing I worked on was trying to come up with different reward functions and ways of sort of abstracting the environment for these agents to make them learn more quickly. Because when I started my PhD, sort of it would require these agents to sort of do years of gameplay nonstop to learn to play Atari games, and I was trying to bring that time down.
Yeah, I remember one of the criticisms at the time was, yeah, it's discovering these nearly superhuman strategies at some of these games, like what was the game where you bounce a ball off a paddle and it hits the blocks at the top
Oh,
and
breakout.
it just break out. And it discovered if
Yeah,
you hit it in the corner, it could go over the top of the blocks and then bounce
yeah,
across the ceiling. And that was incredible. But when you think that it required years of gameplay until it stumbled upon
yeah,
that strategy, and only then was it reinforced, it sort of loses some of its magic.
yeah. But in their defense, you have to realize that these networks are starting completely from scratch, right? So it's not like a human that's had like whatever hundreds of millions or billions of years of evolution that has all these like great priors. These RL agents have to learn to see while also learning to play the game. So it is like a really hard problem. Yeah,
Yeah, that's true. Maybe the fair comparison is between the entirety of human evolution and then one human sitting down and playing the game for a few hours.
yeah,
And then
yeah,
it's not
yeah,
so bad.
yeah,
Then
exactly,
it
exactly.
even seems computationally quite good
Yeah, yeah,
compared
yeah,
to all the
yeah,
computation of the proteins folding, etc.
yeah, yeah.
Um, so, what was the way in which you tried to get RL to be more sample efficient?
Yeah, so I guess one of the main things I worked on was um, kind of the case where the games were, had like infinitely bad sample efficiency. So these games like um, Montezuma's Revenge, where it's almost impossible for the agent to just randomly take actions and then stumble onto a reward or a signal that it's doing the right actions. And that makes it really hard for the agent to learn because it's trying all these different actions. It's never getting any feedback. And so it doesn't really know what to do. And so the way that you try and combat this is you create new reward functions that try and guide it towards this reward function all the way at the end of the game. And the thing I was working on was intrinsic reward functions. So ways of allowing the agent to create rewards for itself that lead it towards the ultimate goal.
Hmm. So, what were these intrinsic reward functions?
Yeah. So the kind of classic flavor of intrinsic reward functions I worked on was called curiosity-based intrinsic rewards. And this is a technique where you give the agent some internal prediction model, and the agent is constantly trying to predict future frames, given its current frame and the action it's going to take. So it's trying to predict the future. And then what you do is you reward the agent for incorrect predictions from its prediction model. And what this does is it drives agents towards unfamiliar areas of the game that they haven't seen before. Um, because in these unfamiliar regions, it doesn't know how to predict the future. Um, and this can be kind of a good sort of prior or incentive to drive the agent towards, exploring the environment efficiently.
Okay, so you've got now two models, one that's controlling the actions and one that's trying to predict what would happen. And the one that predicts
Yes.
what will happen gets rewarded when it's correct. But the action one gets rewarded when it causes the agent to enter an environment where the prediction model fails.
Yes, exactly. Yeah.
Okay, okay.
Uh,
And then
Yeah.
with a game like Montezuma's Revenge, where you have to explore lots of rooms and test things out until you get
Mm.
any points at all, this
Yeah.
allows the agent to have like something to keep it exploring, keep going, keep trying stuff out, even when there's no external reward.
Yes, exactly. Yeah. Yeah. So that was done uh before my PhD. So that was kind of the state of the art. And there's one kind of classic problem with this, which people call the noisy TV problem, which is there will be most likely some regions of your environment that have random or stochastic transitions. And this means they're fundamentally just impossible to predict these sort of the rollout of frames because it's just due to random chance. There's no way to learn how to predict them.
Hmm.
And so this means that the agents can actually get trapped just staring at these random transitions in their environment. Um, and the reason they call it noisy TV problem is because like this thought experiment of what if you put a TV on the wall in one of these environments that just had noisy static, and the agent would never be able to predict the static, and then it would just start of the episode it would just go over to the TV and just stare at it, be constantly getting incorrect predictions, but it'd be rewarding itself because of those incorrect predictions, and that would sort of destroy the exploration performance.
I see. So any kind of curiosity-driven AI is going to get very distracted by these kind of unpredictable elements of the environment. So like a dice or a coin that it could just endlessly toss and be surprised at the result.
Yeah, yeah, exactly. And like all um, curiosity-based approaches try and have some way of guarding against this. Basically, you would train the model to predict what action happened between two frames.
Hmm.
And then you would take the representation from that model. And the idea was it would only learn about things that the agent could affect in its environment. Um, and then that would mean, if there's like some random, uh, tree waving in the wind that you weren't able to predict, because that's not caused by the agent wouldn't get trapped by that. That was kind of the existing technique.
So you've got two neighboring frames, and there was some action that the agent took in between. But a
Yeah.
second part of the AI, like a second network, is trying to predict what action the agent took. And
Yeah.
if that network cannot learn what action the agent took, then that means the transition was caused by some uncertainty that's not due to the agent. It's just randomness in the environment.
Yeah, pretty much. Like the representations you learn to predict which action happened between these two frames are going to be representations that only are concerned with what the agent does. It's not concerned with random things that happen in the environment.
Hmm. Hmm.
Um, and then going forward, use those representations that sort of only care about agent actions as your thing to do curiosity-driven learning with.
I see. So you're not so much concerned with whether that network gets really good at making these predictions. You're just interested in the
Yeah.
kind of representations it forms by trying to make these predictions.
Yes. Yeah. Yeah.
Okay,
Um,
interesting.
yeah. But even that runs into trouble because the agent can take actions which induce randomness in the environment. And if that happens, then they still have to try and represent these sort of random transitions to try and make predictions about them. These predictions will always be incorrect, and then you get trapped again.
Hmm. Okay. So what was your approach to the noise TV problem?
Yeah, so we created noisy TVs that were caused by the agent actions, so they were vulnerable to this problem I just described. And what we tried to do is predict predict the next frame, but also predict the what's called the aleatoric uncertainty in the next frame. So predict the randomness of the next frame that can't be reduced from more experience. And then
Hmm.
our intrinsic reward was the standard sort of curiosity-based intrinsic reward minus this aleatoric uncertainty, which kind of represents the sort of unpredictability of transitions, the fundamental unpredictability. And then the idea is when you go near noisy TVs, you can't learn to predict them. And so your intrinsic reward goes down, even though your prediction error is high.
Can you explain again what aleatoric uncertainty is?
Yeah. Um, so you can just think about it as like your uncertainty that's due to inherent noise or unpredictability in the environment.
Hmm.
Um, so if you have lots of noisy TVs in your environment, your aleatoric uncertainty is going to be high. Um, Yeah.
Okay, so aleatoric uncertainty is like uncertainty that's not due to my lack of knowledge about the environment. It's just
Yeah.
irreducible. It's the environment itself is random.
Yeah. Yeah.
Okay, so any randomness that's caused by my lack of knowledge, that's randomness that's worth exploring to try and understand. But randomness
Yes.
that's just inherent in the environment, I need to leave that alone and not be distracted by it because I'm not going to get anywhere with it.
Yeah. Yeah.
Can you explain how your technique differentiates between those two?
Yeah. The way that we do it is we calculate the total prediction error, which is kind of our intrinsic reward. And then we try and remove um, from that prediction error anything that's related to aleatoric uncertainty. So it's basically we have a standard sort of curiosity-based reward, but then we discount those rewards if there's high aleatoric uncertainty.
And
Yeah.
so there's then a network predicting the aleatoric uncertainty at the same time.
Yeah. Yeah. So it's
Okay,
predicting the mean of the next state and sort of predicting the variance in the next state.
I
Yeah.
see. So the agent following your reward function would notice the TV, get
Yeah.
distracted by it for a bit, but then
Yes.
its uncertainty in what was happening next would decrease, and therefore it would
Yeah.
learn that there's nothing to learn from staring at it for long.
Yeah. Yeah. So what the network tries to do is it can assign aleatoric uncertainty to its predictions, but it's penalized for it. So it will try and make predictions, but if it learns over time that these predictions are just always incorrect, then it will start assigning aleatoric uncertainty.
I see, I see. So it
Yeah.
only does it when it's forced to, and that makes it check to see whether it really is predictable or truly random.
Yes. Yeah. Yeah.
And did it work? Did it prevent the agents from getting distracted?
Yeah, it worked pretty good. I'd say it's still like an unsolved problem, a really difficult problem. But we did some fun experiments where I don't know if you know like the computer vision dataset CIFAR 10, but
Mhm.
it's basically just pictures of like cats and airplanes and cars. I think I got that right, but random natural images. And we did this experiment where the agent could either play the Atari game or it could press an extra button that we added to the sort of Atari controller that would let it just see random sci-fi images, random pictures of cats. And a lot of the traditional methods would much prefer just to watch the pictures of cats because they were totally unpredictable and they were caused by the agent's actions. Whereas our approach was able to sort of learn that those are just totally unpredictable and then continue to explore the environment.
I see, I see. Yeah,
Yeah.
I mean, it seems quite hard to distinguish actually between aleatoric uncertainty and epistemic uncertainty. I mean, there's some things in the environment that look random, like what the weather's going to be tomorrow, but with
Yeah.
careful observations, you can eventually come up with theories and accurate predictions. So maybe the
Yeah. Yeah.
agent, if it was a really intelligent agent learning over very long episodes, maybe it should later on revisit some of these states and see whether it's now able to learn something from what's going on.
Yeah. Yeah. It's like a really, really difficult problem. Humans think they see patterns and things all the time and think they're not random. That people have like superstitions and things like that. And I think like disambiguating whether your prediction's incorrect because like your theory of what's going on is not good or it's just for random noise is just a really hard problem.
Yeah, imagining the agent being like, I've got it, I know which cat's coming up next. I've got the formula,
Yeah.
trust me, guys.
Yeah. Exactly.
Just like let it go.
Yeah.
Yeah, you need to. I mean, it sounds like people trying to predict the stock market, right? If you keep track
Yeah.
of your predictions and the accuracy of them, you'll eventually learn to leave it alone. And it sounds like you've done something similar with your agent.
Yeah. Yeah. And we actually have a hyperparameter that could basically controls how likely they are to assign this aleatoric uncertainty. And it's kind of like, kind of controls this. I think humans have different levels of this, like whether they think something's random or whether they think they've figured out, how to predict something.
Hmm.
Yeah.
That's really interesting. Yeah, I wonder whether that really could be a large personality trait among humans.
Yeah. Yeah. Well, definitely like, humans, different humans enjoy unpredictability more than others, right? Some people really enjoy gambling, for example,
Hmm.
because they can never learn to predict, what's going to happen next. And that is sort of intrinsically rewarding to them. So it's not just agents that have this problem.
For sure. So
Yeah.
you did 3 internships during your PhD. The first one, for a year and a half, you're a research scientist at Copernic AI. Can you tell us a
Yeah.
bit about what they do and what you did when you were there?
Yeah. Um, so I worked with them. They're actually from a UCL professor called Jason McEwen, who's actually an astrophysicist. Um, and basically what they were working on was computer vision for spherical images, and in particular applying them to VR.
Hmm.
So the idea was, wouldn't it be cool if you could put on VR goggles and walk around in these spherical images and sort of experience them as a world? Um, One of the issues is if you don't have good depth perception in these VR systems, as you move around in an image, what your brain expects to see, what you actually see, kind of don't match up, and it makes you feel really sick. And it actually stops a lot of people using VR. And so what we're working on there was trying to create better models of depth perception to make the sort of dynamics of these VR worlds more realistic. And in particular, depth perception in these 3D images. Not 3D, spherical, sorry. Yeah.
Okay, so you've got it's not a full rendered 3D environment. It's sort of
Yeah.
a 2D image,
Flat
but
pixels.
I
Yeah.
see, I see. So
Yeah.
then when you move around this, you sort of it's sort of like moving within a dome with an environment painted on the surface of the dome, but you would like
Yeah.
objects to sort of move around, or there to be some kind of parallax as you're moving around.
Yeah. You like if you walk towards an object, it should get larger, right? Things like that. And if those things don't match the real world, then it makes you feel nauseous.
Mm-hmm. So
Yeah.
what kind of approach did you use on that problem?
So I guess the main thing was because these images are spherical, they're sort of distorted. That means um, traditional computer vision techniques don't work as well.
Mm.
And then so basically what you have to do is do sort of convolutional neural networks that inherently deal with spherical images rather than flat images.
Mm-hmm. And then you get into
Yeah.
tricky maths territory.
Yes, for sure.
So you were also a visiting researcher at Oxford during your PhD. What did you do there?
Yeah. So yeah, the CDT was actually supported me to do a project with Claire Lyle at Oxford. I was really gracious for that. I got to go out there a few times and go to some of their lab meetings and things like that. And Claire is a really great researcher, mostly interested in generalization in reinforcement learning.
Hmm.
Um, and we were also working on a project related to generalization and also different kinds of activation functions you can give to reinforcement learning agents. Um, and in particular, looking at sinusoidal activation functions. So um, basically, you have neurons and their activations are sort of these wiggly sinusoids. And the amount of wiggliness is determined by the weights in that layer. Um, and that's kind of really interesting because you can learn these really high frequency features that learn to represent, really sharp things in the world. Like lots of things in the world aren't these, smooth things that a Rayleigh would represent. So having these sharp features lets you more accurately sort of model things in your network. But because because the features are so sharp, really small changes in the input can lead to really big changes in the representations, and that's bad for generalization.
Mm.
And so what we're looking at is, well, that was kind of our hypothesis, and it kind of sort of turned out to be true. And then we're trying to figure out how can you sort of counteract against that.
So what was the purpose behind sinusoidal activations?
So the sinusoidal activations it basically lets the weights in the initial layer of the network attune the frequency of representations they learn. Um, and because this is like a trainable parameter, they can learn much more complex functions um, and much sharper functions too.
Hmm.
So like Rayleighs are sort of have this inherent bias towards smoothness, um, but that doesn't always work in reinforcement learning, right? Like I don't know if you had like a value. This is very like dumbed down example, but say if you have a function that's trying to represent the value of different states in your environment, and you have a cliff in your environment, you don't want to walk off the cliff, right? So your value function should be like this, and then like straight down, like a really sharp representation. But if you have a ReLU, it'll kind of be like, like curved down, which is not good, right? You want it like, as soon as it gets to the cliff, this is really bad. Like, don't go off the cliff. Um,
I see.
and so by having these tunable frequencies, you can learn these sharp representations.
Is that related to how you can compose lots of sine functions to have uh, almost discontinuities? Like you can take the
Yes.
Fourier series of any function, including one with discontinuities, and then you get some like very sharp corners.
Yes. Yeah. 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 Exactly. Yeah.
Hmm. Do you
Yeah.
still get is Gibbs phenomenon still a problem there? We have this kind of overshoot at the singular points.
Oh.
So I'd imagine when you get near the cliff, it could be the case that just before the cliff, the model represents as quite good, and
Oh.
then it shoots down.
I see. No, we didn't see anything like that, but
Hmm.
that's interesting. Yeah. No.
And then you did a third internship at Redwood Research, which
Yeah.
is
Yeah.
an AI safety company. Can you
Yeah.
tell us what you did there?
Yeah. So there I was working on AI safety, like you said. And at the time, Redwood was sort of concerned that we have these large language models that are really powerful, but we don't know how they work. They're kind of this black box. And that's kind of inherently unsafe because there's no way to like audit the network and try and figure out what it's doing. Um, and the techniques at the time for this subfield called mechanistic interpretability was basically to uh, hire very relatively expensive scientists to sort of go inside of these networks and basically make lesions on the connections in these networks, see how that affected the outputs of the network, and then try and from that kind of reverse engineer, what's the circuit that the agent is using to do different computations.
Hmm.
And then the project I worked on was kind of looking at this and realizing that there's only so many smart people that can do these sort of lesions and try and figure out what the network is doing. So there's some parts of that workflow that we can try and automate. And in particular, we were trying to automate the sort of circuit discovery part of this sort of research you do when you're trying to figure out what a network's doing.
So the way they use the word circuit over there is to mean um, like how the network ties together different concepts and composes them into a final answer. Is that roughly correct?
Yeah. Yeah. Basically, what is, so like you have a transformer, it's got all these different parts to it. And like, what is the subset of those parts that it uses to make a prediction for a given input?
I see. So you don't necessarily identify the concept that goes along with each part, just
Yeah.
the part
No.
of the network. You just want to know that.
Yeah. Yes. So at a high level, what we did is basically had an automated way of like, you have all these different components in your network, and then you say, okay, I'm going to delete this part. And then you look at the output. And if the output doesn't change after you delete that part, then you say, okay, that part's probably not important for making the prediction.
Mm.
And we just kind of systematized and sort of, you know, automated that process of like basically lesioning different parts of the circuit and then looking at the outputs.
And then how much of the network are you able to lesion or zero out ultimately?
Oh, that's a good question. Yeah. Okay. So in the abstract, it says ACD selected 68 out of the 32,000 edges in GPT-2 small. Uh,
Okay.
so it's, yeah, you can delete a lot of the network. I mean, that was for, I think, a very kind of trivial like behavior, but still pretty cool.
So this meme that you only use 10% of your brain, it's sort of true for transformers, even if it's not true for us. That for each particular token they generate, they're just using a very small part of the network.
Yeah, definitely. Definitely. Yeah.
So then the ultimate goal of this would be to try and once you've isolated the part of the network that's doing the work for generating that token, you then
Mhm.
only have to interpret what those components of the network do rather than the full transformer.
Yeah. Yeah. Sort of narrows down the problem to like, okay, this is the little circuit that's doing this behavior. Now it's only 68 edges rather than 32,000, so I can work with it.
Hmm. Hmm.
Yeah.
Do you think it's a, I mean, it's a super ambitious research project. And like you already had so much success with it with being able to chop away so much of the network. But do you think it would eventually lead to safer inference from these networks? Like what's the end goal with this? It's kind of easy to tell a high level story of we want to know what's going on in the network. If we can show that
Mm,
99% of the network's not important, then it makes it much easier to figure out what's going on in the network. But you
yeah.
still got to somehow interpret what's going on, even in that 1%, and then
Mm.
verify that it's actually going to yield a safe output.
Oh, right. Yeah, yeah. No, I think that's, you mean like once you have the circuit, what do you actually do with it?
Yeah, yeah.
Yeah, yeah. Yeah, no, I think that's fair. Um, I mean, yeah, I think roughly the latest approaches, I think circuits in general have like gone out of fashion, but um, I think what you would do is then you would feed that circuit to try and make this more scalable. You could do something like feed that circuit and some inputs and outputs to an LLM and say, what's going on? Um, what's going on here? Which maybe just kicks the can down the road a bit, but I think could work.
It'd be interesting if you could feed it to the same LLM that's being that's being investigated.
Yeah. I mean, I guess like broadly why it's interesting for safety, right? It's like, okay, let's assume that you do have some other way. Like we're trying to tackle like the first part of it where you get the circuit. Let's assume that you have a second part where you can use that circuit to interpret what's going on. The ideal thing would be like, okay, you isolate a circuit for like lying, for example. And you're like, okay, whenever this circuit activates, the model's gonna lie. So we should like probably not use it or something like that. Yeah.
What were the toy problems you were looking at with GPT-2? What kind of sentences was it completing?
I think like the classic one was like indirect object identification.
Oh, I see. Okay.
Uh, yeah. Um, I mean, we didn't look at this one in particular, but like a toy example I know was popular in Mechanistic at the time was like, how does a network add two numbers together? How does it do sums? Um,
Hmm.
how does it, you feed in 2 + 2 and then it says equals 4. How does it do that computation? Those are the kind of like level of like, that's how like toy the problems were. It wasn't like, can you create me a Python repo for this thing? It was very toy problems.
Yeah, I suppose with the lying example, you would hope that the same part of the network would be responsible for causing the lie for every individual lie. Otherwise, it's not super useful. So, like with the adding
Oh,
two numbers, you'd hope that the
yeah.
same parts of the same 1% is responsible for adding numbers every single time.
Yeah, yeah. Or at least you have to have a big enough data set of like line behavior that you use
Hmm.
to do your surgery on the network. You hope that that covers all lies.
Yeah.
um,
Space of
yeah.
all possible lies.
So yeah, 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 yeah.
So after that, you went to New York for another internship at the Cold Spring Harbor Laboratory. What did you get up to there?
Yeah. Cold Spring Harbor is very famous, uh, mostly biology research institution, but is increasingly interested in the intersection between neuroscience and AI. And so there I was working with Tony Zador, who's a famous, like one of the more famous neuro AI people. Um, and we're basically trying to figure out different ways that neuroscience can contribute ideas to AI and make AI perform better, more safely, generalize better, things like that. Yeah.
Yeah, it's maybe the only neuroscience and AI paper I've ever read is one by Tony Zador. Tony Zada.
Yeah, yeah. Yeah, he's great. Yeah.
And then what have you been up to since finishing the PhD?
Yeah. Since finishing the PhD, I'm doing a startup. So this year, I moved to San Francisco to kind of like explore some ideas about what I could do as a startup. And then just recently, we sort of got some funding and things like that we'll announce soon and kind of describe what we're doing. But at a high level, we're trying to make it easier for lots of people to do reinforcement learning. So, like I said at the start, I started my PhD when reinforcement learning was like pretty sexy, but now it's like just like so hot. Like, I don't know. Like all investors talk about is like reinforcement learning, which is very bizarre. Um, and so, yeah, I feel like with my background, it's like, okay, I should have something to say about this and an impact to make. Because I've been thinking about this for a long time.
So RL has taken off, not just with LLMs, but with robotics as well recently. But I guess you're focusing more on LLMs.
Yeah, we're focusing more on like LLMs agents, so LLMs that make tool calls and do things in the world. Less robotics.
So who do
Yeah.
you want to be doing RL? Just more than just researchers?
Yeah. I'd say right now, um, doing RL on your own custom models um, is basically only the labs can really do it. Only the
Mm.
big labs like Anthropic and OpenAI. Um, and then if you're a company making an AI agent, you can't really afford to hire the really expensive people to do it. And you don't really have the expertise internally. And so that just means you can't do reinforcement learning.
Yeah, it's maybe the hardest thing to tune with hyperparameters, etc. RL.
Yeah,
Um,
yeah, yeah.
so you're trying to sort of encode a lot of the wisdom that's been built up into a platform that automates it for you.
Something like that. Yeah.
Am I giving away too much of your secret there?
No, no, that's okay. Um, yeah, we'll announce more soon. Yeah,
Okay, okay. Looking forward to it.
yeah.
What's it called?
Vmax.
Vmax. Okay, I'll look out
Yeah,
for it. Um,
maximum value.
maximum value.
Yeah.
So, in your view, why has RL become more popular recently?
I think the DeepSeek paper had a lot to do with it. For a while, I think RL is a natural, like, okay, we want to go beyond just chatbots. Like, we want AI, well, at least some people do. They want agents to actually do things in the world, right? And RL is a natural way to train agents to take actions and do things. Um, but for a while, it just didn't really work with LLMs. And like, if you tried to train an LLM with an RL loss function, it just didn't really work. But then something's happened recently, and I don't think people really know why. But all of a sudden, RL just kind of started working with large language models. And so now you have this like huge opportunity where there's these LLMs that already have these great priors on how the world works, but they don't really know how to do actions. And then so RL kind of promises to let them do actions. And then if AI could do actions, it's extremely valuable, right? Like if then you can get agents to actually do part of your job for you. That like dramatically increases your productivity, and that's why investors are like super interested in it.
Yeah, I wonder whether it's similar to your initial work on sparse reward functions, where if your LLM is too weak, then it never manages to do anything in environments and so never gets any reward. But once they're really strong, they can start making good guesses, and then it starts bootstrapping up into higher, better behavior.
Yeah, I think that a lot of people are sort of hypothesizing things like that. I mean, there's this thing like the elicitation hypothesis, where it's like, is RL really training the LLM to like learn new behaviors, or is it just sort of amplifying behaviors that already exist in the LLM that already kind of knows and just like pulling those out of the network? Um,
Hmm. Hmm.
and that's kind of similar to what you're saying, I think.
Yeah, it's kind of a bonkers thought that there could be latent abilities hidden in these LLMs. And
Yeah,
it seems so hard to believe that it would be able to do something and yet in some sense refuse. But I think we've already seen that that's the case from the success of instruction fine tuning, where the
right.
base model might just refuse to answer your question or come up with some bizarre response. But if you actually train it, no, I want you to actually follow the instruction I give you, then it starts doing it. These
Yeah,
latent abilities start emerging.
yeah, totally, totally.
If that's the case, it might be that our role would only get you so far. It can only elicit capabilities. It can't actually build up new capabilities. Or maybe when you're
Hmm.
trying to actually build in new capabilities, you end up in the very low sample efficiency regime that we were
Hmm.
previously in.
Yeah,
Could you see that happening?
I can see that happening if we have these sort of the reward functions that we currently have. I think that is the issue. So like, yeah, if you have this sort of long horizon like math problem, and you have to be like reasonably good at math to like guess the right answer at the end. If you can never learn to guess that right answer, then you're never going to learn to solve the problem, right?
Hmm.
But I think if we come up with better reward functions for, I think the technical term is like process reward models, which is kind of similar to intrinsic reward functions, where you sort of give rewards along the way and sort of shape behavior that way. Um,
Hmm.
then maybe we can learn like genuinely new behaviors.
Yeah, I mean, with mathematicians, sometimes you would they would set themselves the goal of solving one problem and end up solving a different one on the way.
Yeah,
Maybe
exactly.
maybe we'll end up having that kind of behavior from LLMs where we're like, oh, okay, well that is good, but it's not what I asked for.
Yeah, I mean yeah, but that could be better than nothing, right? Like at least it solved the first problem, so you should reward them. Yeah,
Yeah, yeah, I suppose that really does call for a different reward function then, because it just counts as a failure
yeah,
on a naive reward function.
exactly. Yeah, yeah.
So one possible risk of RL with LLMs, if it does in fact elicit new capabilities, is that you end up with unexpected strategies for solving problems. Uh,
Mm-hmm.
so if the reward function is solely outcome based,
Mm-hmm.
then it might sort of hack its way to that outcome. And then you
Yes.
have a problem of overseeing all the intermediate steps. Maybe you need another LLM watching over its shoulder, making sure that everything it
Yeah,
does
yeah,
is sensible. Um,
yeah,
do you think that will end up being part of the pipeline for commercial RL on LLMs?
yeah, definitely. Um, I mean, there's like the safety aspect of like, you want to understand how your agent's solving the problem, but also just practically, it's really hard to create incentives for agents. It's like the famous thing like Goodhart's law. I think it's like one example is I forget why, but like at some point in India, the government would reward you for like killing cobras, um, and like bringing the cobra heads to I don't know the government or something. I might be butchering the story, but I think it's like roughly correct. And then what people started doing is breeding cobras, um, so that they could just artificially create a bunch of cobras and bring the cobra heads to the government. And so it's
Yeah.
like uh, incentives. It's really hard to set up incentives to actually get people, either people or agents, to actually do the behavior that you want them to do.
Mm.
Um, and I think that requires like really careful reward design. It is like a huge bottleneck, not only for safety, but also just like actually getting the agents to work. Uh,
Yeah, yeah, they might just fail rather than doing something dangerous.
yeah, yeah, yeah. So yeah, I think that's going to be a big bottleneck. Yeah,
Mm. Mm.
yeah,
Yeah, and potentially make things a lot more expensive to train if you need an overseer LLM
yeah,
or human.
yeah, yeah,
I mean, the classic example is training a coding agent to write some code that passes some tests. And instead of writing code to pass the tests, it changes the tests to be trivially easy to pass, and then writes a
yeah,
trivial function to pass those. And that seems like something an overseer, human or LLM, could easily spot and penalize. Um,
mhm,
but it's possible that if part of the environment is not just the coding environment, but the LLM, a second LLM saying, no, naughty LLM, don't do it that way, then that LLM just becomes another part of the environment to hack. And the
yeah,
goal now is to try and find a way of changing the tests or some other way of fooling the test that this overseer LLM doesn't catch or doesn't notice.
yeah,
And I
yeah,
think
yeah,
we've got really hard problems here to solve if you want to solve them.
sure. Yeah, 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 definitely.
And where do you see this going long term? Like, do you imagine, and perhaps your answer is going to be forced here because you have a startup in the domain, but do you think this is going to succeed and kick off in the next 5 years, for example?
Um, yeah, I think it is already succeeding in a lot of ways. Um, So like software engineering is the most obvious one where it's like, I don't know, I feel like we keep moving the goalposts, but like it's pretty crazy what these coding agents can do.
Mm.
And it sort of dramatically has changed software engineering already, I think. Um, I think the progress will be, it's like the classic thing, like we'll overestimate the progress in the next like 3 to 5 years, but underestimate the progress in the next 10 years is kind of my bet. Um, that slowly these agents will just get better and better, and be able to do longer horizon tasks. But I think it'll be a slower grind than we expect, but it will happen.
Yeah, I think we kind of got a big shock with the release of ChatGPT because a lot of this
Yeah.
research was not really released. People weren't talking about AI at the time anymore, so it looked like a really discontinuous uh, progression. But
Yeah.
in fact, it's being quite continuous. It's just more public now, and this could really creep up on us and start having huge ramifications without there being a singular event like there was with ChatGPT.
Yes. Yeah. Yes. Yeah, it's exciting, but also, yeah, scary times. Yeah.
And do you think it will always be a kind of workmate, productivity enhancer, or do you think we will actually get to the stage where it has such a high level of generalization that it can actually take on full jobs and act as a drop-in replacement remote worker?
Um, yeah, I think for some, like, it's already happening, right? I don't know if you've used like Devin, like cognition software engineering environment. I mean, agent, sorry. Um,
No.
but it's basically like it lives on your Slack, and then you say like, "Oh, can you solve this GitHub issue for me?" Then it goes and makes a PR. Like you don't see any. So it is like a remote teammate, and it
Mm.
doesn't always work, but it's like I wouldn't bet against that. Just getting better and better. Um, or like customer support too is another area where I think whole customer support jobs are starting to be automated by companies like Sierra or Decagon. Um, I mean, yeah, I think you will be a while till we don't need till we have like a fully autonomous company. Like I think you'll often will need like humans to manage these agents. But yeah, I think it's already happening now.
Mm. Mm. Yeah, it's going to be wild times, I think. I
Yeah,
agree with you, though. Within 10 years, things will fairly likely be pretty wild on this front.
yeah, yeah. You've got time though.
We've got a bit of time, yeah.
Yeah, yeah.
All right, it's been great chatting to you, Augustine. I really enjoyed it.
Awesome. Me too.